Ron said, so make sure you have a couple for me. All right, and you're going to halfway close your computers. Actually, log off your computers, and let's go ahead and we'll put those up in rows, but in just a second. Log off your computers because we're going to review nomenclature quickly, and then I'll take some more questions, and then we're going to start with something called compositional stoichiometry. So we have to start at least today, maybe 30 to 35 minutes of it, so that tomorrow can talk about it. Okay. All right, so I'm going to ask for some feedback, okay? So I want you to tell me anything that's going to help guide you to determine the name or something about this type of compound, naming it or writing the formula. Grant, give me something to write under the ionic category. Okay, so the valence electrons help us get the charge of the ions. Is that what you're saying?
Yeah.
Kelsey, give me something else for one of the categories. Okay, so you have to get the charges, which is I think what Grant just said, but what do you do with the charges when you make the formula? All right, so we crisscross charges to get the formula. Evan, give me something else.
8 is the normal number of oxygen. I think it has less oxygen, like 1 mass.
So you have to memorize the 8 version of all the polys, all the polyatomic ions. And if you memorize the 8s immediately, or you already have the ites in hand, because the ites are 1 less oxygen. Hypho, blah, 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 ite is 2 less oxygens. And actually perchlorate, for example, has 1 more oxygen. Okay, so crisscrossing charges, you have to know your polyatomic ions in terms of their 8 versions, and everything else should fall into place. Zane, give me something else about ionics.
Metal and non-metal.
Okay, generally it's a metal and a non-metal. Some of you guys probably saw already there's 1 cation form of the polys, and who is that? Of the polyatomic ions, who's the 1 cation? Say again? Ammonium, right. Ammonium, which is NH4+, is the 1 polyatomic ion that could technically take place of that metal. Since it's a positive charge, it can bond with a negative charge. Anybody else? There's a big gap here in the ionic world. Do we use prefixes? No, so no like generic prefixes like mono, di, tri. So also the middle area on the periodic table, those are called the transition metals, and what do we indicate with them along their name? Roman numeral charge. Okay, so Roman numeral with transition metals, except for which transition metals? Zinc, because it always has a 2. Silver always has a 1, and cadmium always has a 2. So those don't need them since they're an always charge. Okay, so going back from ionic, which like ionic will take you the longest to keep your head wrapped around, but tomorrow your format of your quiz is 5 naming and 5 writing formulas. I think, and this I don't have the quiz ready for me because this isn't like important. But it's going to be around 7 ionic, since we spend like 70% of our time on ionic. 7% of our time on ionic. Gosh, I'm stuttering. Probably 2 covalent in 1 acid, or a combination like that. So it's lesser covalent acids, more ionic. Okay. Say again? Well, we don't see covalence quite as often, so I'd rather prepare you for success later. Okay? So in terms of covalent, what are we looking at in that formula standpoint? 2 what come together? Non-metals, and then how do we indicate the number, meaning their subscripts? Prefixes, do we get charges from the periodic table for this? Do we get charges?
No.
Let's be confident. No, because are there any ions? No, covalents don't have ions, we don't have charges, we don't have crisscross charges. It's going to be simple. You read it, you write it, you're done. Those take like nanoseconds. Yeah, there's really nothing else to write about that. In acids, we have binary acids, and how do you tell me it's a binary acid when you're saying the name? You say hydro, right? So you say hydro, blah, 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 ic acid, hydrochloric acid, hydrofluoric acid, hydronitric acid, and so forth. How do you tell me it's a binary acid? I mean a ternary acid.
No
No hydro, so how do you start it?
Just with the
You name the, what's the second thing though? The polyatomic ion, right? So you're naming the polyatomic ion first. So put the poly ion, and then you'll put but something acid. So the namings of the polyatomic ions control how you name the acid. So if it's an 8 form of the acid, what do you, the 8 form of the polyatomic ion, how do you change the ending? You change it to ic acid. And if it's the ite version of the polyatomic ion, you change it to S acid. Okay, let's take some quick questions from prom set, okay? Yeah. Questions from prom set, guys. Specifically from some of you guys who I have some comments on. Yeah, Evan.
Can you do some of the transition metals ones? Like,
Can you give me an example?
iron phosphate.
Okay. So name the formula to name.
FePO4.
Okay, so FePO4. Everybody should be able to, and this is how I would suggest, at least starting to get the hang of it. You need to just divide this compound into 2 names. So I see iron, I know that's a straight up metal, I have to name that by itself. So this is the first name, and this collectively has 1 name. It's not phosphorus tetraoxide. It's nothing crazy. It's going to be 1 name. 1 name, 1 name. So we have iron, and then PO4 is what polyatomic ion? Phosphate, okay? And I left a gap here because as soon as I realized it was an iron, it was a transition metal, so it needs to have a middle initial, which is going to be its charge. So what's phosphate's charge? Memorize, what is it? No. 3 minus. There's very few things with a 3 minus charge. Phosphate is one of them. Phosphate is a 3 negative, so then what did iron have to be in order to see at the end there's no charges left? Also had to be a 3, so we put a Roman numeral 3 there. So just because there's no charges left here at the end doesn't mean they weren't there at the beginning. So you know that phosphate has a 3 negative, so that meant iron also had to have a 3 plus in order to cross them out and reduce them down. Give me another one. You good? Okay, Cam. Okay. Can I do a similar one?
Well, I'm just confused.
Give
I
me.
got the PO4, but the FE.
So we named our first name first, right? So iron. We named our second name, which is the phosphate. By identification, PO4 was phosphate. And I left a gap between here because as a transition metal, you have to put a Roman numeral to indicate charge.
How do you know it's 3 of them?
Because you've memorized phosphate as PO4 3 minus.
Oh,
Yeah. So then the iron itself also had to have a 3 plus, so that as the 3's crisscross down, we could reduce them both down to 1, because you can indicate here there's both 1s because you don't see any other charges.
So it's a transition metal, whatever, but all that's the same.
Occasionally that works, but not all the time. So for example, tell me the name of write it on your paper. Write it on your paper. I'm trying to be some good examples and I'm moving on. Make sure you're asking me good questions. Do not look at your polyatomic ion list. Try to wean yourself off. If not, you're going to be shocked tomorrow. I'll write a couple more examples up here.
Oh, that's an app.
So 1, 2, 3, 4. I'll scroll up and yeah.
Oh, she can.
So these should be taking you like 30 seconds each.
You have to have the formula.
All right, and let's go through 2 of these, and then I'll put some more examples up here. Raise your hand if you can give me confidently number 1. Like confident. Grant.
Copper 2 chloride.
Good. So, chlor what?
8 chloride.
I can't emphasize that last piece.
Chlorate.
Chlorate. Okay, sorry. So, copper 2 chlorate. So, yeah, make sure you're emphasizing that so that you're understanding that ClO3 1- is chlorate. I could change that and say, okay, guys, let's CU ClO2. And how would you change the name? That would be copper 2 chlorite. And if I change that to 1, that would be copper 2. Say again? Hypochlorite. Good. Copper 2 hypochlorite. Remember, as we take an O off, it changes the polyatomic just a little bit. Okay. Next one, there were 2. Raise your hand confidently. Savannah?
Potassium nitride.
Nitride. Good. So remember, I'd rather use periodic table, right? Ides are coming straight off your table. You just crisscross their charges. No 8s and ites. Yeah, Anthony. Oh, gotcha. I'm ready.
Chromium 3 nitrate.
Chromium 3 nitrate. Good. So we've got a transition metal, we've got our polyatomic ion, and we've named the transition metal's charge by nature of how we uncrisscross the charge to give that 3 back to chromium. So I could change this. What would be the formula for chromium nitrite? Chromium 3 nitrate, sorry. And O. The 2 goes to, 3 goes to a 2. And 3. So this is chromium 3 nitrite. Okay. Raise your hand for the last one. Evan?
Silver chloride.
Good. So silver chloride. Give yourself a thumbs up if you did not put a 1 in there. If you put a 1, thumbs down. You don't have to tell me. So it's always a 1, right? So if you're telling me if you put this is telling me that Miss Emily, you're stupid. You don't know that silver has a 1 charge. Don't call me out like that. So it's this because that tells me we have the same language. We're saying the same thing. 1 charge. Okay. No need to say that separately. Yeah.
So if you put that on the quiz tomorrow.
I'll feel very, very offended and count the whole thing wrong. I get partial credit on these. Okay. I'll get the whole thing wrong.
I put silver 1. That's half a point off.
That's at the half point. All right. I'm going to do a couple more questions.
I was thinking, like at a college level, would they make you put the 1?
Probably not, because it's so rarely forms anything but a 1 charge. Just assumed it's a 1. Okay, so ready for some more?
Yeah.
So 1, 2, 3, 4. I'll get 5 up here.
I didn't even think about that. Oh my gosh.
Okay, so I know hydrogen. So still
I got all the other ones though. Acid or if it's
Anything with H right on. All the rest of it is all
because it's hydrogen. That would make sense.
All right, back to me. What number are we on? 2. You're good. Take a minute. You're good. Take a minute.
Yeah, number 1, 2, and 3. Then what would number 1 be?
No,
And then number 2 no, you need a hydro.
it's a no, it's just because there's no hydro in front of it. That's it.
All right, now back to me for reals. 3, 2, 1. You can self-quiz yourself later, but we're gonna get some feedback right now, okay? So number 1, binary or ternary? How do you tell me it's binary? How do you say it's
Hydro.
You say hydro in order to tell me it's binary. Then how do you name that piece of it?
Nitric.
Nitrogen went to nitric acid. Good. Anything with an H in the front or an H plus in the front is going to be an acid. Nothing else will be named acid unless it has an H plus in the front. All right, binary, ternary.
Ternary.
Ternary, so do you say hydro?
No.
No, you start with naming the poly, which is who? Nitrate. So it goes to nitric. And you remember that how? Ick and I ate too much. Ick and ate go together. This one is ternary. Name this piece first, just the poly first.
Nitrate.
So it's nitrite, and then I have 10 to nitrous, or my chemistry number. So then nitrite goes to
Nitrous.
nitrous acid.
So this it would be like that would be nitrate acid. So every time it's 8, you change it to
Ick acid.
you change it to
Look back at your notes from Friday too. You guys wrote this down like zombies, but you have it in front of you, okay? Now I see hydro. Immediately, what do I know? Binary. So I need to pick out the 2 elements, the 2 symbols. I need to find their charges, and I need to crisscross. Because remember, these act ionically simply because we have to get their charges. So what is H's charge? H is in group 1. It has a 1+ charge. So the acid part of it is telling you that it's got an H in the front. And then the sulfuric is going to tell you it's got a what? S, which is sulfur, which has a charge of 2. So crisscross, what do you get? H2S. That's sulfur or hydrosulfuric acid. And then number 5, you see that it's what?
It's
Ternary. Okay. So you have to have at least 2 elements, or more than 2 elements. What's the very first element always in acids?
H.
So hydrogen ion, meaning H+. So the acid component is actually H+. What does dichromic come from?
Chromate.
Dichromate, which is what?
CR2.
Charge? 2 minus. This is dichromate. This is a polyatomic ion. 8. So crisscross, what do you get? That's dichromic acid. So it's actually dichromium, so it's 2 chromiums and dichromium, which is a dichromate. It's a polyatomic. Okay. Make flashcards for your polyatomic ions, please. Evan, last question. You don't have to, but it helps you to see the 2 pieces. I continue to use polys with parentheses and polys. Yeah. Yes. You crisscross for everything except for covalent. Good question. Because the acids act ionically. Yeah.
If there's a transition metal in there, is it always going to be like
If there's a transition metal that you have to put Roman numerals on, it's always an ion. We never put Roman numerals in acids. Ever. Okay. All right. I need this half the room to put the laptops up. Is your specs right? This half the room to put the laptops up. I'll get back to it. Let's pass this back. So, can I get some military transfer papers on that side of the room? They're right here. Come and get them. Pass them out around that side of the room.
Are we about to take notes?
We're going to take a couple notes, yeah. Today? Not today's whole week. I'm getting notes here. I need one for everybody over here. I'll see if I can get out of my meeting today, but I know the rest of the week I cannot. All right, and sit down. The last half of the room, I'll get you guys in a second for laptops, and then we'll start quick shortly. Izzy, just leave the extras in the back table, okay? All right, so we're going to do a quick review of something called the mole, and this is going to be my intro today. We'll finish this up tomorrow, but the idea is that you have a good conceptual understanding. Did everybody get an honors chem lecture note, chapter 10? Yes. Did somebody get an extra one for Mackenzie? Did you get an extra one for Mackenzie? Emma? Did you get an extra one for Mackenzie? All right, so I'm going to show you a video first, okay? So, good movie watchers? Eyes on the board, you ready? Okay, good movie watchers. This is the concept of the mole, and then we will elaborate. I'm going to ask for you guys to write down a couple of things. I'm going to write some things on the board too, and this might help you pay attention a little bit better during the video. 4.32. 4.32. Let me make sure Pandora's off for a hot second. Grant, hit the lights. Leave the all light on.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. A small furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry.
Guys, I missed it. I gotta go back. Okay. Grant's over there flipping light switches. Alright, so the mole. Title is The Mole. M-O-L-E.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. A small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, just about anything extreme.
The mole, write down this number. 6.02 times 10 to the 23rd. Mole, 6.02 times 10 to the 23rd. We'll talk about what that's referring to shortly.
Really small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Fortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it, particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99%.
You guys understand money. You hear me? Did you understand money? Let's see this example again. Okay, here we go. Hold on. A mole of pennies.
If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is, anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, the mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it. The story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Hey Grant, can you try those lights again? You mind? Okay. Okay, so you'll see I put due chapter 10. There you go. Alright. So reading guide 10 is due tomorrow, but I'm introducing the concept, so actually everything will be quite familiar to you. So you have 30 seconds to turn and talk to the person next to you and tell them what a mole is.
A unit that equals a unit. a unit that equals a lot.
Alright, come back to me, come back to me. Okay, so a mole is, Emma, what's a mole? Okay, so thinking nanoscale, right? We're not going to measure in, maybe measure in grams, but it's smaller than that. We're not going to measure in milliliters, we're not going to measure in pounds, we're not going to necessarily sit there and count things. So we're going to measure in moles, which is a number 6.022 times 10 to the 23rd. Sorry, I have a habit of saying 6.022. That's why I learned it twice in 10th grade, and I just can't get rid of it. 6.02 times 10 to the 23rd, and that's the number of particles. And that is going to be how we describe like matter from here on out. Okay. So as I go through this, think of the examples they just mentioned with like going to the deli counter and going to the store. So mom sent you to the grocery store, right? She says, "Okay, honey, I need a dozen bananas." What are you going to do? Okay, you're going to count out 12 of them, right? What's another way to measure the items at the grocery store? Weight, because there's scales there. So you could say, okay, well, a dozen of bananas, average size bananas, maybe that's 2 pounds. So you get 2 pounds of bananas. So we could mass it. What else could we do?
Measure in price.
In what?
Price. Like $5 worth of bananas.
$5 worth of bananas? Okay, I could do that. So we'll do price, like if you only have $5. You could do mass. You could count them. What's another measurement that we could do to get our bananas? Say again? No, we have to measure it. Another measurement. What have we done in the lab measurements-wise? Volume, right? So you bring your big old graduated cylinder, like this tall, and you go and put some water in it, and you're like, okay, I need 5 liters of bananas. Okay, so you drop bananas in, drop them until the 5 liter mark, and you have water displacement. You could technically do the volume of that, right? Now, ain't nobody in their right mind is going to do that. But technically, you guys have graduate cylinders that big, I want it, okay? But we could do measurements in these ways, okay? So that's the idea, that we can mass things. What will mass generally be unit-wise? Usually in grams. What will volume generally be unit-wise? Milliliters or liters, okay? Counting them, we'll probably go in terms of particles. We're actually going to utilize a number with that, okay? All right, so I probably won't get as far as I thought today, but that's okay. You guys asked me really great questions. Let's write down these 3 conversion factors. Remember that word?
Yeah, dimensional analysis.
Dimensional analysis.
We're not using this.
We are going to use that. It's not immediate for today. We'll get to it shortly. Okay? Yeah. You're going to use it shortly. All right, you guys are not focusing with me, okay? So here we go. Way back when we were doing Unit 1, we were mentioning dimensional analysis. We did that a whole lot. And I said it's going to come back. We took a kind of a breather from it because it just wasn't relevant to talk about last unit, because bonding didn't. And now it's going to be with us basically to stay throughout the rest of the year. So as a quick reminder, thank you for your celebratory comments there. Dimensional analysis was the word that we used for the process of converting.
I don't remember.
I will work with that on everybody, okay? So the process of converting, please no more call-outs because it's a little distracting to the rest of the class, okay? So we're converting from item to item to item to item, and it might be something that we could do from days to years to hours. We could go from pounds to kilograms, but we're actually going to start using some new things that relate to particles, which is related to the mole. So dimensional analysis is the process of converting. Stoichiometry is the actual fancy word for the process of converting, stoichiometry. And I'm hoping that you're stoiched about this. Okay?
You're so funny.
Stoiched. Okay. So Avogadro's constant, we all should know that now. What is that?
6.02 times 10 to the 20.
Beautiful. Okay, so Avogadro's constant, and write this piece down with it as well. This describes the number of particles in 1 mole. AKA, think of 1 dozen. If I say 1 dozen, what number comes to mind? 12. When I say 1 mole, what number should come to mind? 6.02 times 10 to the 23rd, a humongous number. So Avogadro's constant is something that describes number of particles in 1 mole. So that's an equivalency. 1 mole is equal to this many particles. Molar mass, think of what this is kind of saying as you say the word. Molar, what unit comes to mind? Mole. Okay, so it's, let me give the second part of this. What does mass generally refer to? Weight or grams, right? So we're talking about mass in grams. So what we're doing here is we actually have a relationship between mass and moles. So it's the mass that's equivalent to 1 mole of a substance. So you guys still have your periodic tables out? We're going to look at my favorite. Let's go to bismuth. Number 18.
I thought it was silver.
It's just number 1, not my favorite. Bismuth, look at bismuth. What is the atomic mass of bismuth? Approximately 208 grams, right?
Yes.
So 208 grams of bismuth, this is just an example here. 208 grams of bismuth is equal to 1 mole of bismuth. Okay, let's do that same thing and write another equivalency. Let's do potassium. 1 mole of potassium weighs what? Where are you looking? Periodic table underneath the symbol, right? So that's equal to 39.10 grams. So these are molar masses. And we've actually utilized this in our bonding unit a little bit, but these are examples of those and how it relates to the mole. Molar volume is what unit should volume be recorded in? So on milliliters or liters. I'm actually going to use liters here. So the molar volume of something is there's 22.4 liters, and this is what they mentioned in the video. 22.4 liters of a gas, of 1 mole of a gas, sorry. 1 mole of a gas at STP. I'm going to ask for you guys tomorrow to tell me what STP means. It's on your reading guide. Okay? So 22.4 liters. Think about how big that is. Like, think about a 2-liter drink. Yay big. Okay? Times that by 10 to get you around 20 to 11, 22. So it's going to be pretty large. That's how many gas particles, or 1 mole of gas particles takes up in terms of the space, the volume. Questions here so far, guys? So there's 3 relationships. The first one is 1 mole is equal to a number of, what was the number describing? Particles. Okay, and then the second relationship was 1 mole is equal to a certain, what about the substance? Mass of the substance. And then the last one is 1 mole is equivalent to a certain volume of some gas or that substance. So there are 3 mole relationships, and those 3 we will use in our conversion process. And that's it. Like, there's just 3 of them. But understanding how they apply takes some practice. That's what we're going to practice a little bit today and some more tomorrow. Okay. Say again? Oh. All right, so I don't know if you just saw my big bubble map, but I want you guys to draw this with me, okay? Put 1 mole to the left side of your paper. We're going to draw a bubble map. What's up? Somebody's got their hand up. Evan?
Okay, so 20.4 liters of 1 mole of the gas. Is that like every gas or just 1 gram?
Every gas at STP, which you guys are going to know what that is tomorrow. Okay? All right, so you have 1 mole. Make a little bubble map with me. 1 mole. And the first connection, second connection, third connection. So we're going to talk about the relationship here in a second. Let's go and draw another bubble map. Atoms, formula units, and molecules. Atoms, formula units, and molecules. Ain't nobody got time to write formula units.
Is that all we're going to write in the bubble?
We're going to add to this. We're going to add to that. That's why I have some arrows. We're going to add some stuff on those arrows. So this is going to be your BFF right after your polyatomic bound list, but in terms of looking at the relationships of moles. So you've got 3 relationships. All right, so back up to the top, we have 1 relationship, and I've actually taken the umbrella term of particle, and I've broken it down to the 3 things that it actually describes. So particle is just a really generic term like people, and we could get more specific, right? So atoms are going to be one term for particles, and this is going to be only utilized, that word atom is going to be used when we're talking about elements in particular. So an atom of iron, an atom of nitrogen, an atom of bismuth, an iron of strontium, an atom of calcium. Formula units is a specific term for what kind of compounds? Ionic compounds, very good. So this is for ionic compounds. And molecule is a specific term for what? Covalent compounds. Who's answering me there? Thank you. So whenever we start to, this is element. Whenever we start to use the particle terminology, we just want to make sure we're using the right term, just, you know, because it does mean something different. Now, what number relates moles to particles?
6.02 times 10.
So this is a relationship. 1 mole is equivalent to 6.022, or 6.02 times 10 to the 23rd particles, or one of these words that would also be term of a particle. Okay? And then where would you guys find the molar mass of a substance? I'm telling you to memorize 6.02 times 10 to the 23rd, but where would you find the number for the mass? The periodic table. So not the atomic number, but the atomic mass, right? So put PTOE mass here, because what you guys will do is I can say, okay, 1 mole of potassium oxide. Okay, so let's do this example. 1 mole of potassium oxide. So you're writing down potassium oxide. Anybody got a formula yet?
No.
So potassium oxide. Okay. This is not right.
K2O.
K2O, because what are you doing? Crisscrossing charges. Okay, everybody look at potassium on the periodic table. Look at potassium. Potassium, there's 2 of them, and 1 oxygen. So we're basically going to take K plus O. So periodic table, what's potassium's molar mass? 39.1. So 39.1 grams plus 39.1 grams plus oxygen, which weighs 16 grams. So that's like, don't tell me. Is it 94-ish? 94.2? Anybody got a calculator? 94.2. Okay, so basically what you guys just found out by nature of taking a name, writing the formula, taking the formula and breaking into the pieces that it's actually comprised of, we take their molar masses from periodic table, we add them up, and 94.2 grams of potassium oxide is equivalent to 1 mole of potassium oxide. So that's equivalent to 1 mole. This marker is horrible, sorry guys. So molar mass, some masses from PTOE. And that's how you're going to get the molar mass of a substance. Last one, so I just added up potassium plus oxygen's molar mass. 94.2 grams, and that says 1 mole of potassium oxide is equivalent to 94.21 or 94.2 grams of potassium oxide. All right, the last one, what's the number that goes with the molar volume? 22.4 liters. Okay, and we'll only use those for gases at STP, standard temperature and pressure. Okay, so these are the 3 relationships. Thumbs up when I can move on from the bubble.
What is that last one with? Is that an L?
L, 22.4. That's a question mark behind it. 22.4. All right, so this is where it starts on, I think it starts on your paper, am I right? I don't have a paper in front of me anymore. I gave all my kids out.
I do not see.
Okay, not quite. Okay. Yeah. Guys. Okay, so don't have you guys know on your paper just yet then. So the idea is that you have the SI system always at play, so that's where you use specific units all the time. That's what we're learning about the mole. So check, we already know the SI unit for the amount of a substance is 1 mole. The SI unit for amount of a substance is 1 mole, or is mole. And that's equivalent to 6.2 times 10 to the 23rd particles. So that's just the reason why we're learning this. So knowing that, the definition of the mole allows us to convert between what unit and what unit. It's in the question, it's in the written word up here. Between moles and particles, right. And I've already described what the particles' different definitions mean. But one term I've not utilized yet is the representative particle terminology. So representative particles are the three that we mentioned earlier. So maybe where you were writing down molecules, formula units, and atoms, you might want to add just a little bit more detail to that, but we've described it already. So representative particles come in three flavors. Atoms, which are just referring to elements. Molecules, which we've discussed already, refers to covalent compounds. And the word that we didn't write down were diatomic molecules. I want to talk about those in just a second. And then formula unit refers to ionic compounds. So we understand the terminology, and it's just referencing a special type of matter. Now, the diatomic molecules, you guys wrote those down in Reading Guide 8. There are 7 of them. Can anybody tell me one of them? Any takers? Yeah, go for it. Say again? B. It's that side, but it's not B. It's not that far different. So you should know the 7 diatomic molecules. Anybody else? Say again? Hold on. N2. So we'll write that as a diatomic, meaning a little subscript of 2. O2. What else? F2. Keep going. Cl2. Br2. I2. And there's one more. It's not on that side. Hydrogen gas, right? So these are the 7 diatomic molecules. And whenever you have a singular nitrogen, or a singular oxygen, or a singular iodine, one of these, you actually can't write as a singleton. It's actually 2 atoms together. Hence why we're writing a 2 subscript for those molecules. Now, I call it the big 7 in hydrogen. Do you see the big 7? Yeah? N2 or NOFClBri. NOFClBri. It's the big 7 in hydrogen. So I call this the big 7 in hydrogen. Thumbs up when I can move on. Okay, continue for a second there. So what's so special about these diatomic molecules? How do I have to write them? 2 subscriptors. So if I have a singular nitrogen, come on, get it together, Will. Get it together. Okay, you cannot write N by itself anymore. When it's by itself, we actually have to make a little mini-me with it, so we're going to put a 2 subscript.
Wait, why do you have to do that?
Because they're actually not stable by themselves. That's why, like, we drew nitrogen and we did bonding like this. Triple bond. They always take on a diatomic nature. Okay, so there's some diagrams up here that help us to understand how these numbers and these units relate to each other. So first of all, just to backtrack to the diatomics, do you see that this gas right here is a monatomic, meaning 1 atom, 1, 1, 1, 1, 1. That's like neon. It's just a gas just in its singular state. And then this is hydrogen gas, and how are they formed? 2 atoms of hydrogen bonded together, so it's diatomic. Right, so that's just an example of what that particle type would look like. Can anybody name Cr2O7 2 minus?
We're gonna get it.
Shout it out. 3, 2, 1. Dichromate. So when you put dichromate in this form, what's NH42 Cr2O7 ionic compound? What is that? Ammonium dichromate. It's ammonium dichromate. Okay, it forms what? Cr2O3. Cr2O3. It's not an ion, so you can't name it like a polyatomic ion. It's a compound, because it's an ionic compound. Chromium.
Wait,
It's an O.
that's oxide.
That's solid. It means solid. Any guys, come on. Chromium, not quite. No.
Chromium 3.
Chromium 3, thank you. Because it's a transition metal. Chromium 3 oxide. Okay? Alright, so we've got, I'm just reviewing nomenclature with you basically right now. Ammonium dichromate yields chromium 3 oxide, yields nitrogen diatomic gas, and then water. Do not get crafty, it's not dihydrogen, just water. So this is a reaction, right? So what they're saying here in these examples below, you can take 1 mole, so 1 part ammonium dichromate, and it will make 1 part chromium 3 oxide, 1 part nitrogen, and 4 parts water. Well, these things correlate to a certain amount of grams and a certain number of particles. A certain number of grams, a certain number of particles. A certain number of grams, a certain number of particles. What do you notice about when I get to the water one? How different? Like how many times greater than the one before? 4, because the ratio was 1 to 4. So I went from 1 mole to 4 moles, or 4 times 6.02 times 10 to the 23rd to get 4 times as much. So there are ratios present in reactions, all related back to the mole. Yeah.
You can't write it like that. 24.
No, it's just expressing it so that you can see the ratio. That's right. Okay, so this is where I am on your paper. Yes, okay. Do not write this whole thing down. This is a definition. You will write this in your reading guide. Do not write the first part of this down. But what it's supposed to represent to you is we're going to be able to pull information from the periodic table, and we're going to write it right here, and that will give us an idea of how we're using the periodic table with the mole concept in general. Okay, so this definition of atomic mass is related to what we found in the periodic table. But what we learned about, Annabelle, thank you guys, what you guys learned about back in Unit 2 were that everything on the periodic table is actually expressed not in grams, but in AMUs. What did AMU stand for? Atomic mass. So the atoms, their mass, and the unit we use is AMU. So we're not going to really express anything in AMUs anymore, just because it's not a very usable unit. Do I have scales that mass in AMUs? No, what do my scales mass in? Grams. So that's what we're expressing everything in grams, but it relates back to this one average atom of carbon has an atomic mass of 1.0 or 12.01 AMUs, which is 1 mole of carbon atoms, which weighs 12.01 grams. There's a definition, which is the atomic mass unit, and you guys are going to write that down in your reading guide. But regardless, let's look at the PTOE, and you guys look at sulfur, and if I had 1 mole of sulfur, I want you to tell me the mass that it would contain. 32.07 grams. And so we're not going to put AMU for now, because it's just not a usable unit. Okay, look at iron. What is iron's mass, or molar mass? 55.85. So if I have 55.8 grams of iron, how many atoms would be inside of that? No, you're thinking 1 mole. How many atoms are inside a mole? Right, so this number of grams is equivalent to 1 mole. So you could put 1 mole there. Now that wouldn't be right to the answer, it's the question here, but it's a true answer. But the number of atoms that are inside that mole are what? Good, 6.02 times 10 to the 23rd atoms. These are all equivalencies, like 1 foot is equal to 12 inches, things like that. Okay, so now look at carbon, and if I wanted 6.02 times 10 to the 23rd atoms of carbon, what mass would I need of said carbon? 12.01, and where are you getting that from? From the periodic table. So that's its molar mass. So do you realize that we just went through the 3 relationships in that same question? 1 mole, top little branch was particles, which is number of atoms. 1 mole, what was the middle branch? Grams, which we see grams here and here. And then the only one we haven't done is what? Molar volume. So we probably won't do that for a little. Okay? And then I don't know, let me see if I have this below here. Let's do 1 more molar mass problem and then we'll call it a day. Can you guys find the molar mass of H2O? Look on the periodic table. You can do that in your head. Say again? H plus H, because there's two H's, plus O. 1.08 plus 1.008 plus 16, 18.02. Or 016, sorry, 016. My PR table that I have memorized might be a little different than y'all's. It's close.
Do you have to memorize it at college?
01. So y'all's has less sig figs, but it's 1.01. So mine just has a little bit more sig figs, but it's close, right? So molar mass we can do, yes? Okay. Note to self, I will put out a reminder if I can somehow. We have my meeting today. I have a meeting every 3 days this week, so you guys won't see me for a while. But reading guys kind of due tomorrow. So for your quiz tomorrow, I'll put out a reminder I'll be available, but likely it might be like 15 minutes before you get out of it. Okay? Pack up. Oh, laptop's up. Sorry, last folks, my bad. Laptop's up.